CJ on the beat.
What is collision? Ouch! Collision. Let's get to know what are the Newton's laws of motion. Newton's first law states that if an object is at rest, it will continue to do so unless it is acted upon an external force. Newton's second law states that the rate of change of momentum of an object is directly proportional to the resultant force acting on it, and it acts in the direction of the resultant force. Newton's third law states that every action has a reaction which has the same magnitude but acting on the opposite direction. Momentum is of interest during collisions between objects. When two objects collide, the total momentum before the collision is equal to the total momentum after the collision. This is the law of conservation of momentum. What is momentum? Momentum is a product of a moving object's mass and velocity. The symbol for momentum is P. It can be written as P is equal to mv, which is momentum is equal to mass times velocity. Momentum is measured in kilogram meter per second. It is a vector quantity. Let's see what this has got to do with collisions. Elastic collision. This is the type of collision in which both the momentum and kinetic energy of the system is conserved. Inelastic collision, the type of collision in which only momentum is conserved and not kinetic energy.
That's a lot to digest, isn't it? Maybe a bottle of fish will help. Come to me, my love.
I will remember you.
Collision don't just happen out in the open. There's a tiny world that has tons as well. And it's called the world of atoms and molecules. Solids have atoms that are closely arranged and only shake in their places. Packed like a sardine must be awful. Liquid, on the other hand, have a bit more legroom for the molecules. These can move freely, colliding with each other, forming bonds and breaking them whenever they please, like Malaysian traffic this time around. Last but not least are gaseous particles. These particles have a lot of space. I mean a lot. They randomly collide with each other all the time, but don't bond so frequently as much as the other two. But when they do, gases experience chemical changes, a bit mild but significantly nonetheless. These collisions are called effective collisions.
It's hard to know how these gaseous little fellows look and interact with each other. Atoms are fundamentally an assortment of balls, and they make up gases too. Just like all of the life-size balls that exist in us and around us, the molecules of a gas have mass. Coerce them enough and they start bumping and dancing with each other. In this little world, we would have all our little criteria for our little collision idea. Sadly, no. Gas molecules, unlike hard billiards and flying tomatoes, are near invisible and have their own complexities that mess with our idea. Sure, many gases are colorful, but that's as far as our vision goes. Rather, we rely on experimental results to paint ourselves a picture. It's also why we call this idea a theory, realizing it's not universally proven, but brings us somewhat nearer to the actual thing. Ideally, this works for gases under many parameters and conditions. Molecules constantly move and in random directions. Their individual volumes are insignificant to the greater gas itself, because obviously they're all too tiny. We ignore the push-pull forces between them. Again, they're all tiny. They experience perfectly elastic collisions and share an average amount of moving energy. Why these assumptions? It makes the bigger process easier to visualize and measure. It's safe to say that this scenario would be almost the same as every other collision we see in daily life. We've made gobsmacking and atom-smashing breakthroughs because of these assumptions. But we can only sense how these gases behave entirely not their molecular interactions, which is where this ideal theory model plays an important role.